recording. Okay, so today's training will be PostGIS databases and geoprocessing is kind of what I've titled it. It's really an emphasis on PostGIS, which is a spatial extension for a database called PostgreSQL. In fact, it's kind of a goofy name, like PostgreSQL. And this database is an open source database roughly equivalent to Microsoft SQL. It aims to be kind of an enterprise level database that businesses, especially enterprises, could use. But it has also a great developer community in the GIS realm, and they've developed this extension for it called PostGIS. Okay, and what PostGIS does is it adds column types to PostgreSQL that can store geometry and rasters, basically. So we're going to be playing around with PostGIS. Before we dig into it too much, I want to just show you a little bit about databases and about the PostGIS extension, so you have a little bit of context what I'm talking about today. In terms of Tethys, let me just pull up my tabs now, I guess, that we're going to be using. I'll show you the software suite, kind of where this fits in. In the Tethys software suite, we've got PostGIS Spatial Database right here. You can kind of, if you're familiar with the ArcGIS stack, you can kind of think of PostGIS as a geodatabase, okay? It's for storing kind of tabular spatial data. And there's a little blurb on here about Postgres and PostGIS. You can link to the pages I just pulled up here. And we're going to be talking about two APIs. One is the Persistent Stores API, and I'll go into a little bit about why I called it Persistent Stores instead of just Database API. And then the kind of spatial equivalent of that is the Spatial Persistent Stores API. So I'm going to pull that up. We're also going to be doing some more mapping. So that's going to require us to use the Gizmos, the map view gizmo. Okay, so I'll have that pulled up as well. So let me first talk a little bit about databases. SQL is a language that is used to interact with databases. And perhaps a good way to illustrate this is to pull up pgadmin. If you are using the image that we set up for Nephi, you should have pgadmin already installed, and it will have a connection to the database server for Tethys. And it's shown kind of here under the servers. So I'm going to open that up. And you can see right now I have 5 databases in there. Okay, and I'm not going to go into a whole lot of detail about all the different pieces of Postgres. Each flavor of database kind of has their own way of handling things. Usually you have some form of login or user roles so that you can control who has access to the database, but I won't cover that today. And luckily, Tethys, for Tethys apps, you don't have to worry about that. Tethys provides kind of the user management for the database for you, and you'll kind of see that. So I'm going to open up this Tethys default is actually the database for the main database for Tethys. So if I open that up and I expand schemas and the public schema, and here I can see this tables. I don't know what to call that, menu. And you can see all of the different tables in our database. And so if we look at one of these, for example, some of these are Tethys related, like the Tethys services is where all of the credentials for like your CCAN and your GeoServer storage. You can see there's a few different ones. Dataset services are for CCAN. Spatial data sets are for GeoServer. Web processing is for the 52 North extension. So let's look at this spatial one because we have some GeoServer things. If I just click this icon up here, when I've got a table selected, it will just show me the data. And now this should look pretty familiar if you are used to looking at Excel spreadsheets. What databases are composed of, SQL databases anyway, are just tables of data. Usually they have one field called ID, and this PK stands for primary key. That means that it is the unique identifier for each record in the table. So if you're trying to identify a record really easily, the ID is a good way to do that. And then you can see there are a bunch of different columns in here. And if we kind of expand this, you can see that the column has a name. In this case, the name is name, and also a type. So it's a character varying. So in other words, it will hold a string. And it looks like all of these are kind of character varying, but there are other types like integers, floats, Boolean, binary. There's all sorts of types. And so what PostGIS really does for you is it allows you to have one of these columns store your spatial data, okay? And then we use SQL to get the data out of the database. And SQL is very powerful because it allows us to kind of dice and query and get only the data that we're looking for, kind of drill down to the data. And it's very efficient at doing that. Now, luckily for you, you don't have to learn the SQL language per se to work with databases in Tethys, because we use an extension. It's a Python module called SQL Alchemy. Let me just pull up their page. Okay. And in fact, maybe a better way to do this would be to show you if you go to Persistent Stores API in the Tethys documentation, you should see a little blurb about SQLAlchemy. And if I did it right, there would be a link to the documentation. So I guess I kind of have the link here in this object relational tutorial for showing you how to use SQLAlchemy. What this does is it basically lets you perform your SQL queries without writing SQL. You perform it using Python. And I will show you how to work with that a little today. So all these resources that I'm pulling up and showing to you are linked to in the documentation. For the spatial SQL queries for working with PostGIS, we're also going to use a Python library that's actually an extension for SQLAlchemy called GeoAlchemy 2. Okay, and kind of a similar idea, it adds the support to SQLAlchemy for the raster and geometry types. So that's an overview of where we're going. Let's go ahead and launch into it. So I'm going to pull up a terminal. And the first thing we're going to do is we are going to create a new app for our adventures today. So I'll activate the environment. Remember, if you don't have the .t shortcut, you use user lib tethys bin activate with the dot. Don't forget the dot, okay? So either of those will activate your virtual environment for working with Tethys. I'm going to go ahead and change into the Tethys dev directory that we created in one of the earlier tutorials. And if we list this, you can see our other apps are here. I'm going to go ahead and use the Tethys scaffold to create a new app. Hopefully this should be pretty familiar to you now if you've been following along with the different tutorials. I'm going to call it PostGIS App. And I'm going to give it a proper name, PostGIS App. And then I'll just accept the defaults on all the other metadata. And let's clean this up a little bit with clear. And list the directory. So there it is. We've got our PostGIS App project started. So now let's change into that directory and go ahead and install it. And to do that, we run Python, we run the setup script basically, and use the develop option for developing. Okay, clear that, Tethys, manage, start to start our Tethys server, development server. And let's go take a look. All right, there's our PostGIS app. What color will it be? Looks like we're orange again. Okay, so the next thing we need to do, let me show you, I've posted some data for this tutorial in the participants Tethys workshop folder on the Google Drive if you're working with Nephi. If not, then I'll post a link to the data. But we're going to be working, it's this PostGIS Geoprocessing, okay? And if you go into here, what you're going to see are several directories that represent shape files, that contain shape files. This one actually contains a lot of shape files. Okay, and the goal of our app today is we're going to create an app that will have address points and flood extents, and we're going to derive kind of the flooded addresses using PostGIS Geoprocessing. So I've taken all of these shape files. I've given you these so you know where I got the data. I pulled them off of kind of the Utah GIS database that they make available, and I have condensed them into these two CSV files, floodextents.txt and provoaddresspoints.csv. And that will just make it a little easier for us to parse into the database. Now you can read shape files and rasters directly into the database using a few programs that come with PostGIS. I'm going to save that for another day. For now, we'll just parse some basically text files into the database. So what I have done previously is I've dropped those files or downloaded them onto my desktop. And what I need to do is take these two text files in the CSV folder. So I'm going to copy them, and then I'm going to go into my Tethys dev directory. Whoops, clicking all over the place. Documents, which apparently I can't get to oh, there's nothing in documents, that's why. So go into my Tethys dev directory. I'm going to go into the PostGIS app, down into kind of the main project directory. And I'm going to create a new folder called data. And then I will just post those or paste those in that directory. Okay. And the next thing I need to do before I can get working too much is I need to open up a new Sublime project. So I'm going to open a folder. I'll go to the home directory, Tethys dev, and the PostGIS app. And I'll just open that. Okay, I'll close the previous one we were working on. All right, and if we expand this, you can kind of see where that new data folder falls in the project directory with the flood extents and Provo CSV address points. Okay, so in working with the persistent store API, we're going to have basically 4 steps. The first step is to register or request a new database. The second step is to define our data model. A data model is like a blueprint for the database. The next step will be to write a function that will take care of creating our tables for us and also initialize them with data so that we kind of automate that whole spin-up process of our database. And then the fourth will be to execute a command on the Tethys command line called sync stores that will actually carry out the operation of creating the database. Okay, so step 1, let's go ahead and register a persistent store. And actually, let's take a moment to discuss why persistent stores. So when you are working in a website, the data, or I guess websites are kind of transactional. So every time I submit a URL, it processes the request, and you either generate the data you need for that page when it's going to be shown, or you find a way to look it up somewhere where it's being persisted. Any data that's generated kind of during the request, if it's not stored in a database or some equivalent, will essentially just be annihilated after the request has been processed. So in that sense, you kind of have two types of data. You have your temporary data that's either generated or used to construct your page. And then if you want data to persist either across multiple sessions, so if the user does something and they want to save their work and then come back later to the website, or if you want it to persist across pages, you want multiple pages to be able to access the same data, then databases are really the way that you want to do that because they persist. The data is there. So that's why I call this the persistent stores APIs, because it's the way that you can persist data behind your apps to live beyond just the kind of transactional request. So let's go ahead and register or tell Tethys that we want a database for this app. This occurs in the app.py, or the app configuration file. First thing I need to do is import this persistent store object. Okay, and then to register persistent stores, I actually need to create a new method in my app class. And it needs to be called persistent stores. Okay, because it's in a class, it needs to take that self argument. These are doc strings for it. Add one or more persistent stores. Okay, and what this method expects is to, or I guess what Tethys expects this method to return is to return a list or a tuple of stores. So let's go ahead and create a store for our database. So what that means is you can have not just one database for your app, but you can have multiple databases. So we use this persistent store object to define our database. What we need to do is give it a name. In this case, I'm going to call it flooded addresses, since we're working with kind of figuring out flooded addresses. It needs a path to an initializer function. Okay, so we haven't created that function yet, but we'll go ahead and tell it where it's going to be. There's a file in your project called initstores that comes by default, and that's a great place to put these initializers for your persistent stores. So I'm telling it to look in that initstores file, okay, and then the function will be init flooded addresses db. So we'll need to create that function here shortly. And then there's another argument, and that is whether we want it to be a spatially enabled database or not. We want it to be spatially enabled, so we'll just say spatial equals true. And what that will do is it will install the spatial PostGIS extension in the database. Okay, flooded addresses. Things look good there. So that's step one. You register a persistent store. If I wanted another persistent store, I would just create it here. Okay, and you could keep listing them. But I only need the one for this app. Okay, so step two, we need to define our data model. And that's what this model.py file is for. So I'll go ahead and open that up. Okay, and again, we're going to be using SQLAlchemy and GeoAlchemy to define this data model. So let me take care of a bunch of imports first from SQLAlchemy. These things are used to construct our data model and you'll kind of see them being used as we go, and I'll try and explain them as we go. We also need to import something you probably haven't noticed, but there's a little utilities file here. And in here, there's a get persistent store engine method that we can use to retrieve the engines, basically, for our persistent stores. So just like when we were working with GeoServer or CCAN, we needed to have an engine object. We're similarly going to have an engine object for interacting with our databases. So we'll import that get persistent store engine so we can use that. Okay. In my model, I like to define my engine here so that I just have to import it into my controllers, and I don't have to declare it over and over again. So I'll use that get persistent store engine, and all we do is give it the name of our database, flooded addresses. Okay, and that will return an engine, or basically a connection to our database. The other thing we need when we're working with SQLAlchemy is a session object, and that basically will provide us a connection to the database so that we can issue queries and add data to the database. So I'm going to call, so what we're going to do is create something that will create these sessions. So we'll call it session maker appropriately. And we're using this session maker thing that we imported from SQLAlchemy to create it. And what we'll do is we'll bind it to our engine. Okay, the engine kind of has the connection information for the database, and we bind that connection information to the session maker so that it will always create sessions that are connected to our database. Okay, the other thing we need is we need to declare this goofy thing called base. And again, we're using this declarative base object that we imported from SQLAlchemy. I'm not going to explain a lot about this right now. All of our tables will basically be tracked by this base object, so it knows how to create the tables. Okay? So in SQLAlchemy, to define a table for our database, what we do is we define a Python class. Okay? And in this case, I'm going to create a table that will store address points. So I'm going to call it address point singular, and there's a reason for that. And all SQLAlchemy data models need to inherit from this base object that we just created. Okay? And it's going to keep track of this class so that when we create the tables, it will know which ones to create. So we'll say SQLAlchemy table definition for storing our address points. Okay. Now there are a few attributes that you just always assign when you're creating these data models with SQLAlchemy. The first one is, this goofy table name with double underscores surrounding it. And as it kind of, you can guess, it defines the table name in our database. So we're going to call it address points, plural. Okay. And then what we need to do is define the columns for our database. Remember, it's just a table with columns in it. Probably all of your tables should have an ID field, so this is kind of a recipe that you just follow. You can use integer type, and we need to tell it, since it is the main ID for our table, we need to tell it to be the primary key. Okay, so what we've done is we've told SQLAlchemy that this property on the class is going to be a column of type integer, and because it's our identifier for unique identifier, we call it the primary key. Okay, we're going to have other attributes, including the full address. This one's going to be a string type. Remember, our tables had names and types. The names will be the same names as these properties, and then we're defining the types as we go. City, state, Okay, zip code. Okay, so that takes care of kind of our metadata for the points. Now we need a field to actually store the geometry for our points. So I'll call it geometry. And in this case, I'm going to use a GeoAlchemy, this geometry object that we're importing from GeoAlchemy. So I'm going to create a column, and it's going to have a type of geometry. Remember, there are different types of geometry, so this type actually takes an argument. And we're going to say it's a point type geometry. Okay. So the next thing we're going to do to make it convenient to work with this is we're going to create a constructor, which is this underscore init method is the constructor for our class. And we're going to have it take an X argument, a Y argument, and then arguments for each of our properties. Okay. And I just like to label these so I remember. It's our constructor. Okay. And then what we need to do is assign these arguments that they're giving us to the properties of our object. So we do that using the self dot full address. It's going to be equal to full address. Self dot city, self dot state, zip code. Okay, and then the last one, self dot geometry. There are a few different types of data that the geometry object will take. One that we're going to use today is a format called well-known text. Let me just Google that. Well-known text. Well-known text is a standard for defining or for encoding spatial data. So here's some examples. If you wanted to define a point in well-known text, you kind of define this point, space, parentheses, and then the X and Y. Okay, and they have different syntax for the different types of geometry. So we're going to use well-known text to encode our data so the database can use it. The other thing we need to do is we need to tell it the spatial reference to use. Okay, SRID, spatial reference ID. And I'm going to use 4326. More on that in a moment. Okay, and remember from our well-known text, point, space, parentheses. And I'm going to put a placeholder, space, another placeholder for Y, close our parentheses. And then on the string, I'll call the dot format method, and I will just pass it the X, Y arguments that we'll be getting from the user when they call this constructor. See the XY here, XY here. So that will automatically form kind of the XY numbers that we give it into the format that the database can read. Let's talk a little bit about SRIDs. There's a great site called Spatial Reference. .org, I believe. Okay. There are a lot of different ways to declare your spatial reference system. One of the most common spatial reference systems is this 4326. Let me maybe zoom in a little bit on this. Okay. EPSG 4326. What that is a World Geographic System 1984. So WGS 84. And all of these links show different ways that you can basically declare the WGS 84 spatial reference. This is a very useful file or useful web page. So the data that I have in the CSV files, if we look at maybe the address points, you can see they are lat-long coordinates, which would be our WGS 84 projection. So we're just telling the database a heads up that this is a WGS84 projection is what this data is in. So it can appropriately locate them on our map and things of that nature. Okay. PostGIS has great support for spatial reference systems. They've got, I don't know, hundreds, maybe thousands in there. So you can use this spatialreference.org to look up the ID. Okay, that takes care of our data model. So what we did is we defined a table using this class for storing address points, and we defined our columns as properties in that class, and we defined a constructor so that we can easily make new entries in this table. So step 3, we need to create the function that will initialize our database. And if you recall, in our app.py, we told Tethys that we were going to call it this, init flooded addresses DB. So I'll go into the init stores file, and I'll create a new function called just that. And these initializer functions take one argument, or they need to take one argument called first time. Okay. Initializer for the flooded addresses database. It's always good to document your code for people down the road. Okay, and so we need to import a few things from our model.py. So from model, that dot means relative to the same directory this file is in. Import. We're going to grab our engine object, our session maker, because we're going to work with the database, the base, and our data model address point. Okay. And then in the initializers, there's basically 2 steps. Step 1 is to create your database tables. You can't add data to it unless the tables exist. And this is an easy one-liner. This is where that base object comes in. So we call base, and it has a method called metadata, or an object rather, called metadata. And that metadata object is just collecting information about all the tables that we are creating through SQLAlchemy. And we can just tell that metadata object in the base to go ahead and create all the tables. And then we just have to give it this engine or connection with the database. And that's it. It will create the tables. After the tables are created, we want to initialize / add data to the tables. And we use this first time variable to perform this only the first time this initializer is run, so that we don't keep adding data inadvertently to our database and basically duplicating it. So if it's the first time the tables have just been created, let's go ahead and populate it with data. Now, what we want to do is take the data that's in this address points CSV, and we want to add that to our database. So go back to init stores. So first thing we need to do is find the file. I'll use this little pattern that I showed last time when working with data or workspaces. os.path.dir name of the current file. Okay, that will get us the directory of init stores, which happens to be the same directory that data is in. So that's convenient for us. To do that, we need to import OS, because we're using this OS to allow us to find that. Then what we're going to do is just construct our path to our address points data set. request.path.join. Okay, PostGIS After, and from there, so this is the directory we're in, PostGIS After. We just need to go into Data, and then the file, provo address points.csv. Okay, that will construct the path to our file. So the next thing we need to do is read the file into a Python object. So let me go ahead and create an empty list. Address. Oh man, I cannot spell today. Address, points, lines. If you can't tell, I like verbose code. It's kind of self-documenting, meaning all my variable names are long. So I'll open this file in read-only mode as F, and then I'll just take this address point lines, and I'll call on the file object, read it, and then split the lines. So what that will do is create a list, basically, where each item in the list is a line in our file. Okay, and if we look at our file, the top line here, sorry, it's wrapping. I wonder if I can turn off word wrap. There we go. So this first line here is just the column headings for our file. So that doesn't actually have data in it that we need. So what I'm going to do is just pop off that first line so we don't have to worry about it. Address point lines dot pop is the method. So that will just pop it off the list. Okay, so now we've got the file read into a list. Let's parse through that list and read it into the database. In preparation for working with the database, we need to create ourselves a session. So we use this session maker that we imported from our model. And then we just parse through our address point lines, for line in address point lines. Okay, and let me make sure, oh, I haven't been indenting using spaces. That might come back to bite me. Let's see. Well, let's just try and be consistent. Okay, so remember this is a comma separated value file. So to split the file into the different columns, what we need to do is call the line.split, basically call the split method on that line, and we're going to split by commas. Okay. So now we'll have basically a list where each item in the list is a different column in our CSV. So it'll be this, second item, third item, fourth item, etc. We'll call that row. Okay, and now to create a new record in our database, we just create a new instance of this address point object. Address, we'll call it address point. Okay, and if you recall, we made a constructor, so X, and I went to the trouble of figuring out which columns each of these were in, so you'll just have to take my word for it. So X is the first one, so at index 0, oops, have to put a comma there. Y is the second one, oops. And then for the other things we need, the full address is located in the 5th column. Put 4 there because we're a 0-based index here. City is in the 16th column. So I put 15. State is in the 19th column. And zip code is in the 16th, or the 17th column. Okay, so now this will automatically initialize all the properties in our address point, just how we need them. It'll take this X and Y and convert them to the well-known text format. Remember, using this constructor that we defined in model.py. So this is what we just used. Okay, so now SQLAlchemy will create that. What we need to do to add it to the database, we first need to add this new object to our session object. Okay, and it will loop through and basically add one of those objects to the session for every line in our CSV, which, by the way, there are almost 25,000 lines in this file. So it'll loop through those quite a bit while it's initializing. Okay, the last thing we need to do, it's all kind of stored in memory right now. Python's aware of it. Now we need to flush it out to our database. So we use the session.commit to save all of that information in the database. And then we're going to go ahead and close our connection. So session.close. And that will just ensure that the sessions remain open. Or sorry, the connections remain open for other connections to the database that will be occurring. Because there's a limited pool of connections to the database. Okay, so let's go ahead and, so we've done steps 1, 2, and 3. We requested a new database, we defined our data model, and now we've written a function that will initialize. This init flooded addresses DB will initialize the tables and add data to them. So now to actually carry that out, we're going to go to the command line. I'm going to stop the development server, clear this so we have some room to look at it. And we're going to run a command from the Tethys command line called Tethys. Let me widen this a little bit. Sync stores, and then we give it the name of our app, PostGIS App. Okay. Okay, it looks like I have a typo in my code. It tried to run that initializer. Okay. So I need this to be actually split lines. Okay. Now what's happened already, and we'll pause and show you this. If I go back to my database viewer and refresh it, you can see it's created this new database. We now have 6 databases. It is got a naming convention that is the name of the app and the name of the database. So if we expand that, we'll see that it actually created the table, okay, this address points table with the columns that we want. And you can see there's this geometry point type here for the geometry field. But there's no data in it because our initialization function failed. I'll also point out while we're here some of the features of PostGIS. This table, whenever you create a PostGIS enabled database, this table gets added automatically, called Spatial Ref Systems. If we look at it, what it has is, as you would expect, a list of the different spatial reference systems. And you can see that they're listed in here by code. And this is how PostGIS can work with so many spatial reference systems. Okay. The other thing that it adds here is this functions. If you look at this functions menu, you'll see a whole bunch of goofy functions with underscores. But there's also these other ones. And what these are basically geoprocessing functions and spatial data management functions for working with the spatial data in your app. Now, it says there's about 1,000 in here, but a lot of those are just variations on the same function. I counted about 400 or so unique functions that are in here for you to use. These include things that will convert data between formats, like you can get it as a PNG or a JPEG, or you can get it as GeoJSON, well-known text, things like that. But it also includes things for performing operations like clip or intersect, or you can do buffers, kind of your standard geoprocessing functions, calculate distances. Okay, so one of the reasons I really like PostGIS is because of these functions. It comes with geoprocessing built in. Okay, so that was a side note. Our table didn't initialize correctly, so we've got to reinitialize it. There's a typo in my code that I fixed, so let's try it again. Now, since our tables have already been created, I'm going to run the sync stores command, but this time I've got to give it this refresh option. And what that will do is it will drop the existing tables and then refresh the database. So when you're developing a data model, a lot of times you'll be iterating, you'll be adding columns or taking them away and modifying it frequently. This refresh option allows you to easily do that without having to do a lot of manual work in the database. So we'll go ahead and do that. It gives us a warning that it's going to, all our data will be lost, but there's no data in there. So it goes ahead and drops that. Oh, but it can't drop it because we are still connected to it. So I'll come back to this database and disconnect. Okay, these are common things that you'll run into. Let's try it again. Now that I've disconnected from the database, there it goes. It drops it, creates it, and now it's initializing it. It takes a moment because it's going through 25,000 rows to add those to the database. Okay, no errors. So let's go back and look at the database. I wonder if I can, I don't know that I can zoom in and make this bigger. Apologize. View. Yeah, there's not really a zoom in. So I don't know if you can see it, but so we'll go look at that table again, address points, and use the data to view it. Okay, it takes a moment because there's a lot of data in here. And you can see it's parsed all this information into the database. Now the way that PostGIS stores spatial data is in binary format. That's why this looks kind of goofy. So we gave it as well-known text, but it converts that to a format that's similar called well-known binary. So any of your geometry or rasters in the database will be stored in this format. The advantage to using the binary is it takes up a lot less space. And it's more efficient that way. Okay, and we also have our other attributes like the address, the zip code, city, and state. So now that we've got that in the database, let's do some fun stuff with it. I think what I'd like to do is show those on a map. Okay, so let's go ahead and go into our home template, or rather controller, for our home page, and let's add a few things to it. Okay, a lot of this is kind of review, so I'm just going to do some copying and pasting. The first thing I need to do is import gizmos, because I'm going to use the map view gizmo. Okay, and the star just means I'm importing them all. And then what I'm going to do is just, for now, define an empty map. Okay, with an initial view that I've gone through and figured out is centered over Provo. Okay, So I'm just using the map view object. It's going to be 600 pixels high, 100% width, so it'll fill the page. There are no layers right now. And I give it this initial view. We'll have the legend turned on as well. So that's what we've done. Let's go ahead and go modify our home page. So we'll open up Templates, PostGIS App, open up home.html. I'm going to get rid of the app actions. And then I'm going to load my Tethys Gizmos module here for the template. And then I'm going to change the header and also add a map view gizmo. Okay. Remember the map options that are defining this gizmo? We just defined in the controller map options and passed to the context so they'd be available there. Okay, so that page should work in theory. So let's go ahead and do Tethys manage start to start up our development server again. And we'll go take a look. Close these other tabs. Okay, so we've got a map centered over Provo, Utah. BYU is right here. So this is where I'm calling you from right now. Okay, so map needs some work though. What we need to do is modify our controller so that it will actually use the database and then add the points to the map. So we'll go into the controller. To work with the database, I'm going to import a few things from the model, our session maker and our address point data model. We're also going to be working with some GeoJSON formats, so I'm going to import the Python library for working with JSON. Okay, so as we did before, since we're working with the database, I create a session. And before I forget, at the very end of my controller, I'm going to go ahead and close that session, just so I don't forget. If you forget to close the sessions, it'll probably still work for a while, but after a while, if the database gets overwhelmed with connections, you will see your app freeze up. So closing the session is pretty important. Okay, now what we want to do is get the address points out of the database. And to do that, we need to query it. So I'm going to do that using SQL Alchemy. So we use the session object, and it has a method called query. And the way it works is if I just wanted to get all of the records out of address point with all of the columns, I would just call it, basically give it the data model that represents our table, and then call this all method. And what that would return is a list of these address point objects, okay, which makes it very convenient to work with in Python. However, we do not want binary format for our geometry because our map view won't read that binary format. So instead, what I'm going to do is I'm going to call, or just grab the geometry column, okay? And if all I wanted was the geometry column and not any of the other columns, then this is how I would construct the query. But then I'm going to call one of these built-in functions, database functions on that geometry called as GeoJSON. Okay, st_as GeoJSON. And what that will do is on the fly as I'm querying, it will convert that binary format of the data into GeoJSON, which is one of the formats that our map will read. Okay, for address, we're going to have to loop through all of these. For address point and address points, Let me show you what is happening. We'll just print these to the console. Okay, we'll refresh our page, which now takes a little time because it's querying for those 25,000 different points and converting them to GeoJSON. If we look at our terminal, what it has returned is instead, since we're only grabbing the geometry column, instead of returning an object, one of those address point objects, it just returns a tuple with values for each column. And you can see in the first entry in this tuple that represents our geometry column, we've got the point formatted in GeoJSON format. And we've got 25,000 of them. So now let's add those to our map. So to do that, I need to first collect a bunch of GeoJSON features, create a bunch of GeoJSON features. Okay. So in my loop, instead of printing, I'll assemble these features. So for each of these, we'll create a feature. And they need to have properties type, so feature, and geometry, which takes the value from our address point. Okay. Another thing to point out, notice that this looks like a dictionary, right? But it's wrapped in quotes, so it's actually a string. So what we need to do is use the JSON library we imported from Python to convert that to a dictionary, that string to a dictionary. JSON.loads is the way you do that. Address point, and we need to pull out the first element there. Okay, and recall it's because this address point is a tuple, and it only has one item in it, but we still need to access it. It's the first item. All right, then what we need to do is define kind of a feature collection, a GeoJSON feature collection. And for time, I'm just going to copy and paste that. This is actually pretty much straight from the example that's in the documentation. Okay, this is where we tell MapView what the spatial reference is. If you recall, it's 4326, and we just give it this features. I guess what we got to do is append this. We give it this list of features with our information in it. Okay. And then we just need to add that. We need to, create a layer now from this GeoJSON object. Okay, and we do that using again, this is pretty much a straightforward example from the documentation. And the layer, for the options, we give it this GeoJSON object feature collection. Okay, I'll give it a name for the legend, and I've figured out an extent that will be a nice zoom extent. Okay, and then we'll just add this to our layers array in the map. Okay, so let's go look at it. Okay, got an error. Unicode object has no, okay. Dot read. Unicode is a type of string. Dot loads. Man. Okay. Sorry, typos today. Okay, you can see it took some time to load. And that's because we're kind of reaching the upper boundary of, with the 25,000 different points of MapView to work efficiently. You can see it's kind of laggy when I'm moving it. As I zoom in, it handles it a little better. So this is one limitation of doing kind of showing your data this way is if you have a lot of data points, it might be better to have this layer on GeoServer, which will serve it much more efficiently. But I wanted to show you kind of how to do it in PostGIS. So unfortunately, there we go. See, it's kind of overloading my virtual machine, and it's freezing up a little bit. Oh, and I just refreshed it. So it was doing okay last night when I was making this because I didn't have the recording going at the same time. But with it going, my computer's lagging a little bit. So you can see we've got address points all over the city of Provo. Great. So now what we need to do is add our flood maps. Okay? And for that, we need to add another table to our database. So it's back to the drawing board. Go into our model.py. This time, I'm not going to type it out. I'll create a new class to represent a new table called flood extent. It has basically 3 attributes: ID, geometry, this time is a polygon, and a map ID. These flood maps I'm deriving from some work that Scott Christensen did. He basically ran hundreds and thousands of different likely scenarios, and I just pulled a few different ones from his thousands of runs. So that map ID kind of identifies it. In this case, my constructor I'm going to have accept well-known text, and you'll see why in a moment, and the map ID. Okay, but kind of a similar thing. And then we need to go modify init stores now so that it will read in, this time from our flood extents file. And if we look at this, let's turn off our word wrap. It only has about 7 lines, so about 6 different flood extents. And the polygons for these are already in well-known text format. Okay, that's why we're having our constructor take well-known text. So let's go ahead and go to init stores. And what we need to do is import this new data model, flood extent. And then I'm going to insert some new lines kind of between this session commit and session close. And they do basically the same thing. We get the path to that flood extents.txt file. We open the file and we split the lines, pop off the first line that has the column headers, and then we loop through them and create new flood extent objects and add them to the session. Okay, this time this file is a tab delimited file, so I'm using tabs denoted by the /t to split it. Also, this file, the polygon, this well-known text is wrapped in these quotes, so I strip the quote off to make it just a string. Okay, not too much going on there. Let's go ahead and make a new template. Call it flood.html. Okay. And in this template, I'm just going to it's basically the same as our other home template. It's just got a map in it. It's a different header called flood maps. We're using the Gizmo, so we load the Gizmo module. We'll go into controllers, and we're going to create a new controller. Okay. And we'll start with kind of an empty map like we did before. Yes, you can ask a quick question. Let me unmute. All right, we have a question.
Yeah, hey Scott, this is Tim. The quick question was the flood extended. You had mentioned where did you get that data set from?
Oh, right. Yeah, I forgot to tell you that. it's from a model that we built in Provo. And what it's actually modeling is a dam break. There's a dam up one of the canyons here in Provo that's on the Provo River that runs right through town. And so the model was kind of built, and it's not an extremely accurate. It was kind of a case study model or an example model. And we used Geisha to do that. So we kind of generated the flood maps. Sorry. Is that good?
That's good. That's what I needed. So you guys basically built that flood map kind of inundation component yourselves. So
correct.
That's what yep, gotcha. So
yep, and it was an easy one to use because we already had it. So that's why it was we had already run it. I mean, we ran about 1,000 of these different kind of equally probable scenarios on that model to come up with a probabilistic effect. So I just pulled a few of those scenarios for our demo today.
Thanks.
Okay.
Back at it. Sorry.
Great. Good question. Okay. So yes, we created an empty map. And then what we need to do is go to our app.py and create a new URL map for this. So I'll scroll up here to my URL maps method. Okay, and I'm going to call it flood. The URL will be /flood in our app, and the controller is that flood controller I just defined in controllers.py. Okay, I'm also going to open up base.html and change our navigation so that we have links between the two pages now that we have in our app. So I'll just replace that with this. We've got a link to our home page and a link to flood now in our app navigation. Okay, so we'll go ahead and refresh. Oh, now this is where it's coming to bite me. Unindent doesn't match my spacing. Yep, I've got all spaces here. Got a few. So Python is really finicky. If you're working in Sublime, it's good to come down to this tab and make sure you've got the indent using spaces, because it doesn't like when you mix the tabs and the spaces together. So if I highlight it, you can see the spaces are the dots and the tabs are these lines. So I'll just tab in and then tab in again to remove those. Okay, so there's another dedent issue. Line 65. Oh, there we go. Got a space right there. Let's try that again. Okay, here it goes, it's loading points. Now we can go to our flood maps, which is basically the same map. So let's go ahead and write some queries so we can get the flood maps out and show them on the map. Okay, in my controller, I need to import this new flood extent model from my model.py. Okay, again, I create a session because I'm going to work with the database, and at the bottom, I'm going to close it so I don't forget. Then I'm going to construct my query. It's very similar. Flood extents session.query. Okay. Flood extent, we're going to get the geometry column, and we're going to call this st as GeoJSON to convert it to that. Okay. I'm also going to pull out another column from this. So the way we do that is we say flood extent.map ID. Okay. and we'll get all of them, all 6 of them. It's not a lot. Okay, so this one's a little different. What I'm going to do is instead of creating one layer with all of them on it, I'm going to create a bunch of layers one for each flood extent. So let me just walk you through this. Initialize a layers array that we'll add all the layers to. We'll parse through each of these flood extent records. And again, we've got this geometry from the geometry field, just like before. So we define kind of this feature that will define the geometry. We define a feature collection now for just that single geometry. Okay. It expects a list in this feature, so I just put my flood extent feature in that list. It's a one item list. Okay, and then I create a new layer for it. And in the layer, for the title, I'm going to have it say flood extent and the run number, basically the map ID. And I get that from this flood extent, basically the result of our query up here, flood extent, because we're looping through them. .map ID, because we got that field. And then I've got an extent for zooming to the layer. Okay, and then I'll just append each of those layers to this layers object, and then I'll replace this with the layers in my map view. Okay, and that should do it. Provided I don't have any more typos. Oh, you know what we forgot to do? We didn't create our tables again. That's what this is telling us. The relation flood extent does not exist. So let's go disconnect from our database. And, well, hopefully we'll stop the server. And we just need to run that sync stores command again. Let me clear this with the refresh. Okay, and what it will do is it'll drop all the tables and create them again. Looks like we've got a typo. Unexpected indent. I wasn't careful with my spaces today. So let's go here. I knew it was gonna, yeah, see, these are all spaces. Okay, so since most of this file is tab delineated, I will just get rid of these with okay, let's see. Python will get you with those spaces. It's good that this is happening though, because it will illustrate how you fix it. So this file, I never set the spaces, so we're kind of stuck with our tabs. Hopefully it will be okay with that. Okay, so let's try running this again. Yes. Okay, and it seems to be running this time. So again, the problem we had is Python is finicky about how you tab in. You either need to use all tabs or all spaces. It doesn't like it when you use both. Okay, we'll just confirm that that got created like we wanted it to. So we'll go into our flooded addresses database, drill down to the tables, and we'll look at our flood extents. And we've got our records in there, so that's good. Make sure our address points are there too. Okay, and those are good too. Excellent. So now let's start up our Tethys server again. Okay, and now we'll try and refresh this page. And there you go. We've got all of our flood extents on here. So you can kind of see the Provo River flows down this way. Or is it down this? Yeah, I think it's down this way. I think the mouth is right here. our model boundary condition is up here. And you can see because of the blocky nature, Geisha is a structured grid. So it is kind of got this blocky resolution because it wasn't a very high resolution model. Okay, so that is great. If we wanted, we could go and hide the different layers and explore the different maps and do those things. What we've got are basically 6 different flood scenarios that are equally probable if the dam were to break. The dam is up here in this canyon. Okay, this is nice. We're a step closer to having something useful for emergency managers, but what we really need to show them is potential addresses that are flooded. So let's do that. So I'm going to go back to, what we're going to do is create a new view that will show basically will allow it to show one flood extent and the addresses that are flooded on the map. So for that, we'll create a new URL map. And this URL map will have a URL variable in it. In this case, an ID that will associate with the ID in the database of the flood map. Okay. And we're going to create a new controller called flooded addresses. So let's do that. Let's go to our controllers.py. Okay. To save you watching me type a lot, I'll just go ahead and copy and paste it and walk you through it. So, flooded addresses is the controller. Notice that in addition to the request, since we have a URL variable, it will take this ID argument. Okay, we create a session so that we can work with the database. In this case, I'm going to grab the flood extent that we want to show on the map, but instead of grabbing all, I'm going to grab just one. And I'm going to filter it by this ID column. If you recall in our model.py, our flood extent data model has 3 columns, ID, geometry, and map ID. So I'm going to filter it by that, and I'm just going to say I only want the one that's equal to whatever gets passed to the URL. Okay. I'm also grabbing the geometry, converting it to GeoJSON as we did before, and the map ID. But this time, instead of grabbing all of them, I'm grabbing one. Okay, and what this one method at the end of this will do is if there isn't one, it will actually throw an error. It will only allow it to go through if there is one and only one. So that's kind of a check for us to make sure that it worked how we expected it. Just like before, this is pretty much the same as what we did before. We create a feature with this geometry in it. We create a feature collection that has the coordinate reference system defined, and we create a layer for it. And the layer is going to have the name flood extent with the run or map ID. Okay. Now, so that will take care of showing the flood inundation area, the flood extent. Next, what we need to do is we want to show the address points, but only those that are flooded. So to do that, we're going to use one of the geoprocessing functions, intersects. Okay, so we'll just grab the address points that intersect with our flood area. And to use that, this function takes well-known text as an argument. So I will use basically query again for my flood extent, again filtering by ID. But instead of getting the geometry as GeoJSON, this time I'm going to get it as text or well-known text. Okay, this well-known text does not have the SRID string before it though, so we add that right here. Okay, then I perform a query on the address points. I'm going to convert the address points to GeoJSON so I can show them on the map. I'm going to filter them by this intersects function. So I only want the address points that intersect with the well-known text of this flood extent. I'm going to grab them all. And then, so it's kind of a tricky query, but after we've got it, we've just got a list of addresses. So just like we did in our first controller, we assemble a new layer with those address points. So I'm not going to review that. Okay, and notice that we're using the same flood.html template because all we need on there is a map, and that template has a map, so it works. We're going to go to our base.html and modify our navigation a little bit. We're going to add to it a new category called flood scenarios, and we'll have a link to each scenario. So to generate that URL, I called the URL map flooded addresses, and then I'll just have an argument for each ID in our table. Remember, if we look at our table, the IDs that I'm talking about, oops, that's our address points, are these ones here, 1, 2, 3, 4, 5, and 6. So I just, in our navigation, to make it easy, I create a link for each one of those, and I call it scenario 1, 2, 3, 4, 5, 6. That'll make it easy for us to access them. Okay. So let's just refresh flood. And now we've got our different scenarios here. Click on one of them. And since we're not loading nearly as many points, it's a lot faster. Okay. So now you can see we've got only address points in this particular flood area. Okay. Let's go to the biggest one. They're kind of in order of flood extent size. So now we've got all these address points. Point out that, let's see, let me orient myself. Here's the Provo River coming through. And right through here, this is the street I live on. So looks like we just narrowly miss, according to the worst case scenario that we found, getting flooded. Of course, that depends on how much I trust this model, but I'm pretty close to this flood extent, so for better or for worse. Okay, so that's good. Unfortunately, we can't click on these addresses and see them, and there's a lot of them, so I don't think I'd want to do that anyway to see what the address is. So the last thing we're going to do is we're going to create a page for each of these scenarios that will basically list the addresses that maybe a emergency manager could print out or use to make decisions from. Okay, so let's go ahead and go back and create a controller for this list page. So we'll make a new controller called list. And what we're doing in here, again, we're getting a session to work with the database. We query the database, again, for the text so that we can use our intersects function. Then we're going to get our flooded addresses, but this time, I'm not worried about getting the geometry. I'm interested in all the other information, like the full address, the zip code, the city, all of that information. So I'm just going to grab the entire record as is. And I do that by just putting the model. It will return all the columns. And then what I do, and I'm filtering again by only those addresses that intersect this flooded area for that scenario. Then I'm going to pass that list of flooded addresses and also the ID to the template. Okay, I need to modify the template so that it will, instead of showing I need to create a new template rather. Called list.html. And in this one, it's just going to list the address. So in a for loop, I've got an unordered list here. In a for loop, I create each list item, and I just call the different properties of that address object to assemble my address. Okay, full address, city, state, and I forgot the address dot zip code. Okay, so it'll be kind of a bulleted list. I'm also showing the scenario ID here in the header. Okay, and then on the flood map on this page, I'm just going to create a link here in my app actions to show the list. So I pull up a scenario and I want to see the list of the addresses. I just click on that link. So I'll go back to my flood.html, and what I'm going to do is just add this app actions block back here. And if the ID is defined, then I'll go ahead and show this list button. Because recall, this flood.html is being used by two different controllers. In one case, you have the ID being passed from the URL. In the other case, you do not. So we only want to do this if ID is being defined. Okay. I also need to go back to the controller for that, the flooded addresses, and I need to pass the ID to the controller so that we can use it to create that link. Okay, last thing we got to do is go into our app.py and define our URL map for this new list view. Okay, called list. It's very similar to our flooded addresses. It takes the ID, our URL variable, but this time we append the list URL parameter there. I'm just going to call this list controller. So let's refresh our page here. Looking at scenario 3. Now I've got this link. Let's pull up the address list. And here you go. I've got a list of addresses for all those homes that would be flooded. And thankfully, my home is not among them. So that is our app. Okay, so I'll open up the phone lines. I guess phone lines. I'll take you unmuted and ask for questions.
Yeah, Scott, this is Tim again. Quick question on just the kind of the intro part that you were doing with your databases from the basic parts of the streamflow prediction tool. The data sets that I'm getting, that I'm pulling into both my Rapid as well as my ECMWF,
yeah.
those data sets are setting where within my original watershed that I created to give me my forecast. Those are also part of the database, right? So that's your base maps that you're working on. So where would those data sets be setting that I could be able to see those data sets?
Well, I think perhaps this is a question maybe I could answer in more detail offline, because it's pretty specific to your use case. And to be honest, I'm not extremely familiar with the Streamflow app because I didn't make it. That was a colleague of mine that made it.
Gotcha. Okay. Well, that's fair enough. Yeah.
There is a video that we did when we were talking about CCAN.
Yes.
I posted a video about that talks more about working with the repeat data sets. And those are a little different than the database that we're working with here.
Okay, I just didn't know if that was setting in the same databases if we wanted to try to create an inundation map like what you were working with. So I was just trying to figure out where those data sets were versus the data sets that you were working with today, especially since you were using your flood extent, and so the models that you had already created was what you pulled in, and that made perfect sense.
Right. So to generate the flood extents from the rapid data, you would have to run it through some sort of model. We are not currently doing that at this point, and that's one of the things that, one of the improvements that the NETHI summer camp we were seeking to have happen is right now we basically have stream flow, and to get the flood extent map, you'd have to run it through some hydraulic model like HEC-RAS or perhaps a 2D model, SRH or something. And then, yeah, the output from that, or even Geisha, right? You could use Geisha to do it, like I have shown here. But then the output from that, you could read into a database like I've done here and use it to intersect address points as I've done here. One thing that I would point out is in all of this, when I was doing my intersecting, let's see if I can find, I guess I got to go to controllers. So for example, I'm using this intersects method. It takes well-known text. It doesn't matter if that well-known text comes from the database like it was here. If our flood extent was, for example, sitting on GeoServer, we can actually pull out the data as well-known text in addition to other formats. So you're not necessarily constrained to using just PostGIS to do an application like I've shown today. The purpose of today's training, though, was PostGIS, so I tried to do it all in PostGIS. But you could kind of mix and match, and it will really depend on what the format of your data sets are in natively, what the best solution will be.
So Nathan, I guess that's my question. Could you better define the difference, like what situations are this PostGIS better for and what situations are better as using a more static GeoServer?
Sure. So PostGIS is great for like our address points to a point, no pun intended, where you've got a lot of tabular data. Like think of data that you would store in Excel spreadsheets. Okay, that's like tabular data. Databases are amazing with that, and they are fine-tuned to be really fast for working with a lot of tabular data. Now you can see in terms of mapping a lot of points from a PostGIS database, we really got laggy when we were showing all 25,000 points. So there's kind of an upper bound to how much I guess the map can handle coming in that format. And there's a lot of reasons for that I won't go into. So you kind of got to make a judgment call there. When you start getting to this upper bound, then you might want to start thinking about using something like GeoServer, because GeoServer will handle those larger data sets a lot more efficiently on the map. It will render them basically as a single image, which the web page will load almost instantaneously. So that's kind of, I mean, at this point, I'm seeing this map be laggy. It even froze up for a bit while I was showing it. I would say I would move this data set to GeoServer and try and work from it there, if that makes sense. Now, the tricky part with that is to query and get only, for example, like on these maps, to get the similar map where you have only the points that intersect the flood inundation area, you won't be using SQLAlchemy like I showed today. Instead, you'll be using some of GeoServer's filtering capabilities. And it does have an intersect method on that filtering. So it's just a different tool, a different process. So I guess to answer your question, if your data sets are small enough, then PostGIS is a great solution because it's a little easier to work with than the GeoServer option, and it'll handle that data pretty well. And you can kind of operate it on like you would or like a Excel spreadsheet. You're kind of used to thinking of it that way. But once your data sets start getting pretty large, then that's when you want to start thinking about maybe doing a GeoServer, which is a little more robust solution for those.
All right.
Does that make sense?
It does.
The other thing that I don't have right now support for is these GeoJSON layers. You notice they're all the same color. There's no way to specify the styles right now for these layers. Hopefully in the next version of Tethys there will be. But with GeoServer you can style it a little more and make things pop out.
Cool.
Any other questions?
If there's a time, Scott, that I could just chat with you offline with kind of my question with some of the others with the stream-flow prediction tool, that'd be great today or tomorrow.
Yeah, let's set up maybe a Google Hangout to do that. I might be able to do it this afternoon. Definitely I'll have some time tomorrow, so maybe tomorrow morning would work best for me. But why don't you shoot me an email? Yeah, and we'll set that up. Again, I'm not super familiar with that app. Maybe what I ought to do is connect you with someone who is, or have him participate in the Hangout as well. So.
Yeah, either way, that would be great. And I don't want to burn any more of your time, but if you would know even the person that I can contact, I'm about ready to shoot you an email, and we'll follow up with that.
Okay, great. All right. Well, with that, I'm going to call it a day.